So we're starting with our module 4, that is nothing but design and realization of IIR filter. Okay, so we have studied the designing part and the realization part of our FIR filter. That is nothing but your finite impulse response, and here this IIR stands for infinite impulse response. Okay, so we'll go for studying some design techniques, okay, that are meant for such filters, okay, designing and realization of such IIR filters. Okay, so basically you know what is a filter, right? Like it is used to uh, uh, limit the unwanted signals or noises that you have, and it allows to pass through the signal or enhance the signal that is of our interest. Okay, so as I said here, this module will discuss about certain design techniques wherein the desired frequency response, okay, the frequency response that we would require is basically calculated by the transfer function, and this transfer function, uh, how is it expressed? It is expressed in terms of polynomials, that is you will have a ratio. Okay, you will have the numerator as well as the denominator terms. We'll see just a little bit of theory before we enter into the main part of the chapter. This is essential for you to know. Okay, all right. Now this transfer function, okay, the transfer function that we are talking about here, okay, in the design techniques, this will yield your impulse response for the infinite duration. Okay, therefore the filters, that is nothing but the analog filters that we are designing here are called as your infinite impulse response filters. Okay, so you have a transfer function. Why do you require this transfer function? In order to obtain the desired frequency response. Okay, this will be in terms in the ratio of polynomials, okay, wherein you will have your numerator as well as your denominator. Numerator is related to your zeros, denominators are related to your poles. Okay, that we'll see. Okay, now this transfer function gives you what? It gives you impulse response which is infinite for a particular amount of time, okay, for an duration. Okay, so that duration is infinite. Okay, the transfer function that we have, it yields an impulse response of infinite duration. Therefore the filters that we are designing here will be called as the infinite impulse response filters. Okay, so a typical design procedure for the IIR filters, okay, it follows certain steps. Okay, steps in the sense like what are the things that you basically will have to do. First thing would be you will have to have a transformation method, okay, that would do what? That would map the specifications of your analog filter into the digital one, which approximately should give you the same frequency response. Okay, that is the first thing. And the second thing, you would convert the specification of the digital IIR filter into the corresponding equivalent specification of your analog IIR filter. Why? Because after you perform the mapping, after the designing, when you map from your analog to digital filter, okay, this digital IIR filter should meet the frequency domain specification that we have mentioned here initially. Okay, and what is the third thing? Designing the analog IIR filter in accordance with the transformed specification. And the fourth one would be you are transforming the analog filter that we have designed into a corresponding digital filter, which will be basically used. Okay, so we are designing, we have certain analog filters, we are finding some parameter specification out of it, using some transformation techniques, that specifications will be converted for the digital filters. Okay, so those transformings will be helping the analog filter to be converted into the corresponding digital filter. Okay, so we would talk about this analog filters first, then we have some transforming techniques. Okay, so different topics we have on these. Okay, all right. So there are basically two main classes of analog filters that we are going to study. We are going to concentrate on. One is your Butterworth, another is your Chebyshev filter. Okay, these two are your analog filter. First, we would talk about the designing of these filters with respect to various characteristics like your cutoff frequency, like your order, okay, all that. Okay, then we will study about some transformation techniques wherein these analog filters can be converted into an equivalent digital filter. Okay, so two analog filters we are basically going to concentrate. One is the Butterworth, another one is your Chebyshev filter. They say familiarity with these filters will help us to choose this filter class for a specific application. So depending upon understanding these filters, you will be, depending upon the application requirement, you will be able to decide which particular filter suits it. Alright, okay. So, you know about your FIR filter that we have studied as a whole chapter. Okay, so FIR filter is basically non-recursive where the the present output depends only on the present input, whereas your IIR filter are your recursive ones where the present output, okay, depends upon the present as well as the past input samples. Okay, alright. Now the impulse response. Okay, we are more interested in the impulse response because for FIR it is finite, for IIR it is infinite. Okay, alright. So the impulse response for a filter which is realizable in nature will be, you can see it is with respect to some limits. Okay, h of n equal to 0 for n less than equal to 0, and for the stability condition summation n equal to minus infinity to plus infinity mod of this h of n is less than infinity. Okay, now how does the transfer function of an IIR filter basically looks like? Okay, so h of z, we had this in the FIR filter. Okay, so this is basically for the FIR filter. Okay, any digital filter for that matter, it would look like this. Okay, but when it comes for the IIR filter, the transfer function is defined in terms of the, I told you, ratio of polynomials. Okay, so this particular above term, the numerator gives you the zeros, the denominator parts gives you the poles. Okay, so information regarding the zeros, information regarding the poles. In FIR filters, if you remember, we have no zeros. Okay, we have poles, we have coefficients basically. Okay, all right. Okay, see, now we'll talk about some specification of the analog filter. Okay, that basically we are interested, that is nothing but the pass band ripple, stop band ripple, that is a attenuation, the cutoff frequency and all that. Okay, so this is a frequency, magnitude of the frequency response. Okay, for a range of frequency indicated by your omega. Okay, so you see the ideal frequency response for any filter, okay, for that matter should be 1. So you can divide this into 3 different regions. One is pass band, transition band and stop band. Okay, so the ideal filter should have a stop band just after this pass band, but in practice it does not happen, right? So you should obtain, you will have your frequency response, the maximum as 1 here. Okay, but that does not happen, that is in the pass band, that is, there should be a smooth passing of the signal, correct, but due to some ripples, okay, due to some ripples, or if I have to generalize much and tell you, it is nothing but the noise or the attenuation. Okay, it is reduced to 1 minus del p. Okay, so this is for your omega p, that is nothing but the edge frequency of your pass band. And similarly for the stop band, what happens, ideally you should not have any signal passing beyond it, but what happens, due to the noises, okay, ripple, it is reduced to this particular point and indicated by del s. Okay, so you can see here the mathematical description of the frequency response. So this, if we have to represent mathematically, how would we do? H of j omega, that is nothing but the magnitude of the frequency response, okay, will be between 1 minus del p to 1. Okay, that is, it is lying in between this when your omega is between 0 to omega p. Okay, and it is between your 0 and del s, that is, it is greater than 0 but less than del s, that is this particular region that you see when your omega is greater than your stop band frequency. Okay, that is something but your omega is. Okay, so these parameters you have to be very familiar with, because it is very important, because in the problem you will have you will be given values of few of this to calculate the characteristics of your Butterworth filter. Okay, which will be the first topic that we'll be discussing here. Okay, so this del S and del P is nothing but your tolerance of the magnitude response in the pass band and the stop band respectively. Okay, see, the desired magnitude response is ideally 1, but that does not happen due to the presence of some noises or the ripples. Okay, so what is this AP? AP is nothing but passband ripple or the attenuation. You can remember this as passband ripple. Okay, this 1 minus del P is also passband ripple, but when you want to express this in decibels, in dB, okay, we term that as AP, and that is if you have this particular value, taking minus 20 log of 1 minus del P will give you the passband ripple in dB. Okay, similarly, taking minus 20 log of del S will give you the stop band attenuation in dB, and we represent that as the stop band ripple here. Okay, and this Kp and Ks is nothing but the gain, and Kp is given as minus Ap and Ks is given as minus As. Kp is a gain at omega equals to omega p. Similarly, Ks is equal to minus As for gain at omega equals to omega s. Clear? Okay. So you have several ways of classifying your analog filters, okay, depending upon their magnitude frequency response, depending upon their cutoff frequency, shape of the amplitude response, phase response, or the nature of devices that you're using it on. Okay, so this is we basically concentrate more on, that is magnitude frequency response. Okay, so if you have to categorize that with respect to the magnitude frequency response, we would do that as your low pass, high pass, band pass, and band stop, that we have already seen. See, this is low pass, high pass, band pass, and band stop. This is what actually we obtain, and this is what is a ideal. Okay, an ideal filter should have, see, the ideal low pass filter should have this would be the starting of the pass band, and this is the ending of the, so it should allow the low frequency signal in this particular band, but ideally what happens, this does not happen. Okay, it sneaks through. Okay, that is, it does not stop at this particular, even there will be what do you say, passing of the frequencies even beyond that particular point. Similarly, high pass filter, see, it should limit the what do you say, low pass signal and low frequency signal, and allows the high frequency signal to be passed through, but again it does not happen, sneaks through this region also. Band pass allows only a particular region, so if you consider the low frequency here and the high frequency, some particular range, so ideally it should be this. Okay, but what happens, again, see, it has an extended part here as well as here. Similarly, band stop, okay, again some range of frequency, but here this is the ideal one. Here again you can see it extends to this area as well as this area. Okay, so this is what is of our interest basically. Okay, and this is what we have discussed also. Okay, so these are a few more ways in which you can go for classifying your analog filters. Okay, so depending upon the magnitude of frequency response, cutoff frequency, the amplitude response, phase response, and depending upon the devices you are incorporating it into. Okay. Now, when do you call a filter as a normalized filter? Okay, the filter will be normalized the cutoff frequency. You know that at omega p, okay, that is, if you consider the edge frequency of the pass band, at that particular point an ideal filter till that particular point only your ideal filter should allow the signal to pass through. After that it should stop, but it does not happen. Okay, so what do? So we obtain a transition band in between the pass band and the stop band. So we consider a frequency in between this transition band called as omega c, that is nothing but the cutoff frequency, and we assume the signals are passed till that particular point, and beyond that there are no signals. Okay, so if a filter has to be called a normalized one, then the cutoff frequency of the filter should be equal to 1 radian per second. Okay, and you can obtain your low pass, high pass, band stop filter, okay, by very easily applying the transformation techniques that we would be studying later to a particular normalized low pass filter. Okay, all right. Now again, okay, if you have to design of digital filter from, I told you the first uh, introduction part itself. Okay, in the first sheet itself I told you that you will have certain transformation techniques wherein you would be converting your analog filters to the digital. Okay, so here you see design of digital filter from the, so what are we basically doing? You map the desired digital filter. You see the second step first, derive the analog transfer function from the analog prototype. This is what we will do, because using the Butterworth and Chebyshev filter. Transform the transfer function of the analog prototype into equivalent digital function. Then come here, map the desired digital filter specification into the equivalent analog filter. Correct? Okay, so what is their interest, what are they trying to do here? So you know that you have an analog filter and you are going to transform that into the convert that into the corresponding digital one. Okay, so first you are trying to understand the specification of those digital filter to which you want to convert. Okay, so that you can work on the analog filter, that is, it is you are working on the output, the desired. So you get to know, so if you are asking a customer what basically you require, you understand the requirement and then you start a workflow towards it, right? It is the same thing. Okay, so map the desired digital filter specification, so you understand the desired digital filter specification. Okay, then you try to map that into corresponding or equivalent analog filter. Then you derive the transfer function, okay, for the analog filter from the prototype that you have designed, okay, from the filter that you are designed. Okay, then you transform that transfer function of that analog prototype into the digital one. Okay, so go through the steps once or twice, you would understand, okay, along with what I said now. Okay, all right, so let's start with the first kind of filter here that we are going to see. So first we would see certain important characteristics of this Butterworth filter. Okay, then we would do some problems based on this. So chances are there that most probably the problems only will be asked from this particular topic, but even then, in case if they ask you the derivation for the cutoff frequency, okay, the number of the order that you will have to calculate and all that, you should be knowing this part as well. Okay, all right. So see, Butterworth filter, they say like it has a very smooth pass band. Okay, but you have to pay this smooth pass band by compromising at the transition region. So you have a smooth pass band, but you end up getting a very wide transition region, and exactly opposite of this is for your Chebyshev filter. Okay, that is, you will have a smaller transition band, that is a very sharp transition band, but the pass band will not be very smooth. Okay, all right. Now the magnitude frequency response of your Butterworth filter will be given by this 1 by 1 plus omega by omega c to the power 2n whole to the power 1 by 2. Okay, where what is this n? N is the order of the filter, which depends upon the number of poles. Okay, all right. Then omega c, it is the cutoff frequency. Okay, it is the cutoff frequency where the magnitude of the filter is 1 by root 2 times the gain at omega equals to 0. Okay, 1 by root 2 times, this is the magnitude response. Okay, magnitude frequency response of the Butterworth signal for any order. Okay, n equal to 1 to n equal to 10. They say, okay, this omega c, assume it to be omega c here. Okay, it is defined as the cutoff frequency where this frequency, magnitude of the frequency response is 1 by root 2 times the gain that you obtain at omega equal to 0. Clear? Okay. Some observations are made from this particular graph. It states that h of j omega, okay, this h of j omega is equal to 1. This particular value, h of j omega, that is when omega is equal to 0. Okay. Okay, that is when h of j 0, this is 0, okay, is equal to, the value is equal to 1 for any order, that is any value of your capital N. Okay, all right. Second observation what they make is h of j omega is equal to, this is what they have given the statement here. H of j omega is equal to 1 by root 2 when omega is equal to omega c for all the finite value of n. That means 20 log base 10 of this is equal to your 3 point minus 3 point, that is minus 3 dB you can consider. Okay, that is at omega equals to omega c. Okay, this frequency response will be, magnitude of the frequency response will be equal to your 1 by root 2. Okay, you have the power diminished by a 3 dB value. Okay, and when this is equal to 0, okay, when this particular value will be equal to 0, when your, that is this frequency response will gradually come down to 0 as your omega approaches to infinity. Okay, all right. Now differentiation of, okay, each of the magnitude characteristics is said to be maximally flat. This Butterworth filter is also called as maximally flat. Okay, response filter. Okay, why? Because differentiation of this particular frequency response, magnitude of the frequency response with respect to your omega, okay, will be equal to 0. Okay, for value of small n, you have your n here, your small n here. Okay, for value of any value of your n taken from 1 to 2n minus 1. Fine. Okay, this h of, again, this h of j omega is monotonically decreasing function. Okay, this is you see a gradual negative slide. Okay, that is, see, mathematically again they have represented, if that is h of j omega 2 will be less than h of j omega for any value you consider for omega 1 and omega 2. Okay, so these 5 points are some observation they have made out of that graph, and they are just talking about the magnitude frequency response of the Butterworth filter. Okay. Now we'll start with the main discussion regarding the Butterworth filter. Okay, alright, some little derivation. we'll just go through. Okay, all right. Now they say the magnitude squared frequency, the magnitude of the squared frequency response of the normalized filter, normalized in the sense like omega c will be equal to your 1 radian per second. Okay, for a low pass Butterworth filter will be given by 1 by 1 plus omega to the power 2n. Okay, now this can also be written as hn j omega. Okay, hn minus j omega. Okay, this is modular 1 by 1 plus omega to the power 2n. Now if you replace this, that is if you replace this j omega by s, okay, so that is j omega is equal to s in the left hand side. Okay, what would you obtain? H of n s, h of n minus s equals to, now instead of this omega, so j omega is equal to s, so omega will be equal to s by j. Okay, so at the right hand side you are replacing this omega, so 1 by 1 plus s by j to the power 2n. Okay, now they say the transfer function, this transfer function has no finite zero, and therefore this h of n itself will have no finite zeros. Okay, when this thing itself has no finite zero, this see, this is indicated by the, but you will obtain the poles. Okay, this was for 0, the what do you say, the numerator was for 0 and the denominator was for your poles. So how would you obtain the pole? You would obtain the pole by equating the denominator to 0. Okay, that is what we will see here. Okay, we'll see. Okay, now the characteristics of commonly used analog filter, maximally flat low pass filter, that is maximally flat. I told you the Butterworth filter can also be called as a maximally flat low pass filter. Okay, that is its characteristics. Okay, all right, now this we know. Okay, the ideal filter should behave, it should, the magnitude frequency response should be 1 for the pass band and for the stop band. So we just we know that it does not stop at the pass band, so we consider the cutoff frequency. So we assume it allows the signal to be passed through till your cutoff frequency, and beyond that it just stops. Okay, see, that is what it is. The above filter passes all the frequency for omega less than equal to omega c, and this will be the pass band of the filter, and the filter blocks all the frequency for omega greater than omega c, and this will be the stop band of the filter. This omega c is the cutoff frequency. Okay, now come back again. Okay, now the magnitude squared, right? We had this, okay, h of j omega square 1 by this thing, and again we had this s, okay, that we will replace this j omega by s, so h of s whole square is equal to 1 by 1 plus omega by omega c. See, there it was just in term of omega. Now for this particular, okay, this particular what do you say, approximation, filter approximation, okay, we are obtaining the transfer function as this. Okay, we are going to obtain the transfer function as this. Okay, for that we are starting with this particular frequency response. Okay, so it also includes the cutoff frequency. There it did not include the cutoff frequency here. Okay, so we told you the significance of the cutoff frequency here. We are not considering omega p here. We are starting with omega c. We end up getting omega p and omega s. Okay, that we'll see. Alright, so we are replacing this by s. So h of j omega, okay, mod of the square, so this will be h of s mod of square, okay, by 1 plus omega by omega c whole to the power 2n. So this is written as h of s, h of minus s 1 by 1 plus omega by omega c to the power n. Okay, now same thing what we had done here. Okay, so we would want to make some changes here. Okay, what is that? So s is equal to j omega, right? J omega. So if we square on both sides, this will become s square by j square omega square. So s square by j square will be equal to your omega square. Okay, which can also be written s square by j square. J square will be minus 1, so omega square can be written as your minus s square. Okay, and why do we need this? We are going to take this square term. we are going to open this square term. So h of s into h of minus s is equal to 1 by 1 plus minus s square. Hope it is square. Hope it is understood. Omega square is equal to minus s. Minus s square by omega square c to the power n. Okay. Now how are you obtaining the poles? The poles of this is obtained by comparing the numerator, comparing the denominator to 0. I told you. See, 1 plus minus s square by omega c square whole to the power n is compared to 0. So minus 1's come to this side. Okay. Now what is happening here? What is happening here? We have an n here. I have missed that n here. Okay. So your minus s square by omega square c will be equal to minus 1 whole to the power 1 by n. Clear? Okay. Now another consideration is, assume e to the power j 2k plus 1 into pi, okay, for k value equal to 0 to n minus 1. Okay. Now e to the power j theta, e to the power whatever j theta you have, you will write, if you have to write that, you will write that in terms of cos and sine. How will you write? Cos theta plus j sine theta, right? So theta is just 2k plus 1 pi, so you have cos 2k plus 1 pi plus j sine 2k plus 1 pi. Okay. Now 2k plus 1 into pi for the corresponding values of the k would result into, see, if you change, consider the value of k for 0, 1 and so on, you would end up getting some values as pi, 3 pi, 5 pi and all that. Okay. Clear? See, first value you can substitute, this will become 2 into 0, so 1 pi. Okay. So pi, 3 pi and all that. Okay. So if you cos pi plus j sine pi, cos 3 pi plus j sine 3 pi, cos 5 pi plus j sine 5 pi, if you consider this, okay, if you calculate this, you will end up getting the value minus 1 plus j 0. Cos you will get, for the odd values of pi, you are getting minus 1 plus 0. Okay. And so this has no meaning here, so we can write it as minus 1 always for k equal to 0, 1, 2 to n minus 1. Clear? Okay. Now we had this, right? Minus s square by omega square c minus 1 to the power 1 by n. Correct? Now instead of this minus 1, we can substitute this e to the power j 2k plus 1 pi. So we have written e to the power j 2k plus 1 pi whole to the power 1 by n for the value of k equal to 0, 1 to n minus 1. Okay. So again, taking this s square is here, taking the denominator to the right hand side, omega square c into e to the power j 2k plus 1 pi by n. Okay, you have this pi, you have taken this pi out, and this minus is also this side. So omega square c. Okay, so omega square c. So how did we get this? So s square is equal to, we had this, nothing we have done. Okay, this is minus 1, minus sign is there, this minus is taken to this side, so minus 1, we have written this as minus 1 omega square c into e to the power, the same terms remain. Okay. Now when we take square root of this, what happens? This becomes s, and this becomes plus or minus root of minus 1 omega c, okay, e to the power j 2k plus 1 pi by n whole 1 by 2. Clear? Okay. Now what is this? Since root of minus 1 is equal to j, correct? No? J square is equal to minus 1, so j will be equal to root of minus 1. So we are going to replace the value of this root of minus 1 by j. So we will have sk. K is nothing but for all the values of k starting from 0 to n minus 1 plus or minus j omega c e to the power 2k plus 1 pi whole to the power pi by 2 and 2 you have taken it here 2n. Clear? Okay. Now again, e to the power j pi by 2 will be cos pi by 2 plus j sin pi by 2, which will be again 0 plus 1j. So e j pi by 2 will be 1j. So again we are going to split this particular term. Okay. So what are we doing? Sk is equal to plus minus uh, uh, omega c e to the power j pi by 2. Okay. So where did this j disappear? See here, e j pi by 2 is equal to j always. So instead of this j, we have replaced it by e j pi by 2. So plus minus omega c, okay, e j pi by 2 into e to the power j. This whole terms remains as it is. So now we will take e to the power j common. We will get pi by 2 plus 2k plus 1 by 2n pi. Clear? Okay. Now, if omega c is 1 radian per second, we had considered a normalized low pass filter. Okay, so we had considered a normalized low pass filter. In that case, we will write sk is equal to e to the power j phi k, where your phi k is nothing but this entire term. E to the power j phi k, pi by 2 plus 2k plus 1 by n pi for value of k 0 to n minus 1. Okay, same thing, we have just made it short. Okay, okay, e to the power. Where did this term go? We don't see this omega c here. Why? Omega c is equal to 1. It is a normalized filter. So we end up getting sk is equal to e to the power j pi by 2, this whole term. Okay, and this we have written it as phi k. That's it. Okay. Okay. Now we will calculate those poles. Okay. All right. So how are we calculating that? Okay. See, this equation gives the pole position of your Hs. We started with Hs and H of minus s, right? We started with the magnitude frequency response, the square of the magnitude frequency response, okay, and we ended up getting this. Correct? Okay. Alright. Now, for the filter to be stable, we have to consider the poles on the left hand side of the j omega axis in the s plane. So, if you consider the s plane, okay, so for in order to get a what do you say, stable filter, okay, we will consider the poles on the left hand side of the axis. You would have studied this zeros and poles in the signal sense system, hopefully. Okay, all right. These poles becomes the poles of h of s. Okay, the poles that we are going to calculate will become the poles of your h of s. Okay, so let us assume n equal to 1. The order is 1. Omega c is okay 1 radian per second. Now s naught is equal to e to the power j phi k we have, right? Okay, now k, what is k for n equal to 1? Okay, your k starts from 0, right? See, k value starts from 0 to n minus 1. So n is 1, 1 minus 1 is 0. Okay, so it is just value of k is just 0. So what is your phi k? Your phi k is pi by 2 plus this whole thing. So we have written it here, wherever you have k, we are replacing it by 0. Pi by 2 plus 2 into 0 plus 1 by 2 into 1 into 5, and you end up getting pi by 2 plus pi by 2 equal to pi. Correct? Okay. And so this pi is nothing but this phi naught. So e to the power j pi is equal to minus 1. Okay. So you are obtaining only one pole, and that is nothing but 1 by s plus 1. Now when you consider n equal to 2, okay, so your k will be 0 and 1. N is 2, 2 minus 1. So you have starting from 0, the k value 0 and 1. So you will have this e to the power j phi naught as well as e to the power j pi 1. So wherever you have k, you will replace 0 as well as you would replace it by 0 as well as 1. Okay, so for 0 we have calculated, but there will be a difference in the value down here. Okay, it is looking back. K equal to 0, S naught, it is see for phi naught it is 2 into 0 plus 1, 2 into 2. Okay, n is changing, do not get confused. And in the previous one the value of n was 1, here the value of n is, here the value of n is 2. Okay, so for k equal to 0, you end up getting it as 3 pi by 4, that is e to the power j 3 pi by 4. Okay, s naught. Similarly, S1 will be, when you are replacing your k by 1, n is again 2, you are getting 5 pi by 4. So S1 is e to the power j pi by 4. So again cos 3 pi by 4 plus j sin 3 pi by 4 for S naught. For S1 it will be cos 5 pi by 4 plus j sin 5 by 4, 5 pi by 4. Okay, so you would obtain the value as S naught as minus 1 by root 2 plus j 1 by root 2 and minus 1 by root 2 minus j 1 by root 2 for your S1. So you will have two poles. So h of s will be given as 1 by s minus s naught, s minus s1, that is nothing but replacing the value of s naught and s1 as this, you would obtain this particular value. Okay, so we call these as the Butterworth polynomials. Okay, for different order. Okay, these are the polynomials. Okay, so for order n, 1 we calculated, it had one pole, s plus 1. For 2 you had two poles, you obtained s square plus root s plus 1. Okay, so we are considering the poles at the left side of the j omega axis. Okay, so you have your 1, 2, 3, 4, 5. If you calculate for all this value with respect to these, okay, that is it, however we have done for 1 and 2, you would obtain these values. Okay, now how are you determining the order, that is a capital N and cutoff frequency omega c of the Butterworth filter, given some values of your AP, AS and all that. Okay, that is a ripple in passband ripple and stop band ripple. Okay, given all those value, how are you calculating your cutoff frequency and your order? Okay, that is nothing but n. This order is nothing but number of stable poles that you have. Okay, that we have seen. Okay, when n was 1 you had 1, and when n was 2 you had 2 stable poles. Okay, alright, now some considerations let us make. Okay, so let AP be the maximum passband attenuation we have seen. Okay, the ripple, okay, in dB, which will be at frequency omega p. A is minimum stop band attenuation in the in dB, where at the stop band frequency omega s. Okay, now again we are going to define this in terms of omega s and omega p. Let's start with the pass band. Okay, so h of j omega will be given by 1 by 1 plus, okay, epsilon square into omega by omega p to the power root of, this was square, okay, root of, see we are coming back to that. H of j omega square equals to 1 by 1 plus omega epsilon square into omega by omega p into 2n. Now you take log on both these sides. Okay, you are taking log on both these sides. What will you get? Okay, so log 10. Okay, log 10 is it is, so when you take logs is 10. Okay, 10 into 2, this becomes 20 log h of j omega. 10 log 1 minus, so numerator and denominator, when you take log you basically get something like this. Okay, 10 log 1 minus 10 log of whatever you have here. Okay, they have just diagrammatically represented this. Okay, so we would make use of our what do you say, the pass band, and for the stop band we are bringing two new terms for the purpose of representation, but that is nothing but your epsilon and your pi. Okay, alright, and where is your AP and AS existing? You see, this is your pass band, this is your transition band, this is your stop band. Okay, so attenuation Attenuation in the stop band is represented by AS. Attenuation at the pass band is represented by your AP. Ideally it should be 1, which is not. It is reduced to 1 by root of 1 plus epsilon square this, okay, and 1 by root of 1 plus pi square for the stop band. Okay, alright. So from figure, okay, the omega equals to omega p, that is at this particular point. Okay, the attenuation will be equal to AP. Okay, therefore now the equation, okay, that is nothing but this. The above equation is translated into 20 log h of j omega p is equal to AP. Okay, this becomes 0 is equal to, that is attenuation of the pass band, okay, equals to minus 10 log whatever you had here. Okay, so AP is equal to, you can write this as, okay, you see here, omega is equal to omega p. Okay, omega is equal to omega p. So you have replaced in this above equation omega by omega p. So omega p it gets cancelled. So 1 to the power 2n, anything to the any power on 1, you will obtain 1 itself. So we can write it as AP is equal to minus 10 log 1 plus epsilon naught, epsilon square. Okay, so minus AP by 10 is equal to 10 log of this, that is you are left with only this term, 10 and minus you have taken this, that is nothing but minus 0.1 AP here. Okay, so again when you take inverse log, you can see here, so 1 plus epsilon square will be equal to 10 to the power, okay, 10 to the power minus 0.1 AP. Therefore epsilon square is equal to 10 to the power, this minus 1 is being taken here, epsilon will be equal to root of 10 minus 0.1 AP minus 1. Let it be here. Let this, the calculated thing of epsilon be equal to this. Similarly, now you are going to replace this omega p by omega s in this particular equation. Okay, so when you do that, what would you obtain? 20 log of this, a is equal to 10 log 1 by, now there is no cancellation yet, here there will be a 2n, okay, 2n, I have missed here. So your a's will be equal to minus 10 log, that is this becomes 0, minus 10 log, this is there as it is. Now you see what are we doing? Again as by minus is here, as by minus 10, okay, that is minus 0.1 a is equal to log of this. So 1 plus this term will be equal to 10 to the power minus 0.1 as. Okay, same as what we have done. So epsilon square by epsilon square into omega s omega p. There's no cancellation of this term, so this term looks little bigger than the previous one. Okay, so this will be equal to minus 1 will go here, you have your minus 1 here. Now instead of epsilon, okay, what we had there, we would replace the value of that we have calculated here, okay, in this particular equation that we have obtained. What would we get? Omega s by omega p to n, this root of, you have written this as 1 by 2, okay, 10 minus 0.1 AP minus 1 by 2, so this, okay, so epsilon is this, that is 10 to the power minus 0.1 AP minus 1 into 1 by 2 into 2, because it is square of it, okay, so into 2, okay, equals to this 10 to the power minus 0.1 as minus 1, that is here, okay, this particular you have equal to. So now this will be equal to 1 by 2 into 2, this gets cancelled, so this entire term becomes the denominator to the right hand side, okay, so omega is by omega p to the power n, this root of this n, you are left with this. Now again taking log of this, n log of this, log of right hand side, n will be equal to log of this entire huge term divided by log of omega s by omega p. Now we will simplify this particular equation. See, we normally don't get this values in integer. So whatever value we obtain for n, we were calculating for n, right? We tend to round it off to the next higher integer value. Okay, all right. So n is greater than or equal to whatever you have done. Rounding off is there. Okay, and it is written as log of let us assume it to be as your pi, and this was our epsilon. Okay, so n greater than a log of pi by epsilon. It is not clear here, this epsilon, by log of omega s by omega c, wherein your epsilon is equal to 10 to the power minus 0.1 ap minus 1, and your pi is equal to this. Okay, root of. Okay, so again, so for simplicity of notation, we define the parameter a and k as a is given as pi by e. That is, again, for further simplification of the notation, that is, this term they are going to represent as a, and this term they are going to represent as k. Okay, see, omega p by omega s is your k, but here it is omega s by omega p. So if I have to represent omega s by omega p in terms of k, it will be 1 by k. Okay, so n greater than equal to log of a divided by log of 1 by k. Okay, all right. So this would be your n, the value of n, that is the order you will be calculating using this. Okay, now if you have to determine the expression for omega c, that is the cutoff frequency, what you have to do, again we would start from the beginning, that is h of j omega whole square by, that is square of the magnitude frequency response will be equal to 1 by this. Okay, same thing that we had, 1 plus omega square, we know this. Okay, this also we have seen, this also we have seen for the squared magnitude frequency response. Okay, now equating on both sides. Okay, see, equating left hand side is equal, so right hand side we are equating. So 1 by 1 plus omega by omega c whole to the power 2n by 2n will be equal to this particular. So right hand sides are being equated. Okay, so both are 1 by 1 by, so I can write this as 1 plus omega by omega c whole to the power 2n by this equals to this. Now what are we doing on this? 1 is gone. Epsilon square omega by omega p into 2n is equal to omega by omega c 2n. Okay, so now again omega 2n omega, these two terms can be cancelled, so it is cancelled out. So omega epsilon square. Okay, what are we left with? You see? Okay, epsilon square is equal to, alright, this two have been cancelled out, so we are left with omega p by omega c. Correct? Epsilon square is equal to, this is being taken here, so omega p by omega c whole to n is equal to epsilon square. And what is epsilon? Root of 10 to the power minus 0.1 ap. So it is square, so you can write it as this. Okay, so now omega p, we are removing this epsilon square. Okay, so omega p whole to the power 2n, omega c multiplied by omega c to the power 2n multiplied by this particular term. Okay, you can see here. Then again we are taking omega c, that is omega c will be equal to elaborated steps, that's it. Okay, so very easily you can do it, nothing else. Omega c to the power 2n will be equal to omega p to the power 2n divided by this particular term. Okay, we are not stopping there, but this is not only our cutoff frequency. Okay, now what are they doing? Now omega s by omega p to the power 2n is equal to this. Okay, now again further solving this. Okay, you will obtain both see, one calculated with respect to your omega p, one calculated with respect to your omega s. Okay, so here we are calculating with respect to your omega s. Similarly, it will be for your omega p also, and we end up. You just go through this. You just go through it, you will understand. It is all elaborated step. So omega c will be equal to omega p by 10 to the power minus 0.4. So if it is the edge frequency of your passband, so that's why the attenuation is AP here. Here it is for stop band, so the attenuation of your stop band here. Yeah, so this is the expression for your cutoff frequency given your edge frequency of your what do you say, pass band as well as for your stop band. Okay, so finally the steps for designing your analog butterworth filter will be whatever given specification you have to find first the order. This you would make use to do your problem. Okay, next thing that we'll be dealing will be your problem only. Okay, so whatever n you obtain, if it is not an integer, you have to round it to the next higher value. From there you find the transfer function, that is h of s for omega c equal to 1 radian. Okay, considering a normalized filter. Okay, you have to calculate the cutoff frequency, then you would find the transfer function h of s for the above value of the cutoff frequency by substituting s is equal to s by omega c in h of s. This you would understand better while we solve the problem. So kindly go through the derivation, understand how we are obtaining the poles, how we have obtained the equation for n. Okay, that is the order, how we have obtained the equation for your cutoff frequency, and also go through the introduction theory part.